Okay. Um, on behalf of this GAN course, I would like to welcome Mithun T. Agustin. Uh, brief bio about Mithun Agustin. Mithun Agustin is currently a postdoctoral research fellow in the Process Control Laboratory within the Department of Chemical and Material Science Engineering, University of Alberta. Prior to this, he served a postdoctoral from IIT Bombay from March 20. Recently, he has served. Okay. During his time, he worked on the machine learning based on process monitoring and deep learning based systems identification. Mithun has received his PhD degree from IIT Delhi, where his interests include design and analysis of stabilization model predictive control schemes for switch systems. He has completed his MTech from the College of Engineering, uh, Trivandrum 2017, and BTech from Electronics and Communication Engineering from Government College of Kannur. His research interests include control system, model predictive control, electrical engineering, process engineering, applied mathematics, and data science. Okay, yeah, this is a brief view about the and because of this GAN course, I'd like to welcome Mithun Agustin sir, and we would like to welcome you through through sampling, but this is also virtual to you. Okay, yeah. Can you
Yes, yeah, I can. Yeah, thank you, everyone. Thank you, Professor Surender, for inviting me. Yeah, so my name is Midun. I am currently a postdoctoral researcher at the University of Alberta. So in today's talk, we will be mostly discussing on neural network and how we can use neural network for extracting static and dynamic models from data. So I
Mithun
think
sir?
I will share the screen now. Yeah. Yeah.
Yeah. Uthar sir, we'll every 10 minutes or 15 minutes we'll have a small pause because it's online interaction. So that any queries or anything like that, we'll have an online interaction.
Sure, that would be fine. Yeah.
Every
Yeah.
15 minutes, something like that. After
Yeah.
completing particular slots of yours, we'll have it. Okay.
Okay, sure.
Thank you.
So is the screen is visible?
Yes, sir. It's
Okay,
visible.
okay. Yeah. So yeah, in today's talk, we will be mostly discussing. This is the overview. So like we will be start discussing on the basic concepts of neural network. So where we will discuss how we can use a neural network for approximating functions, nonlinear functions. Then we move on to state space neural network, which is basically a neural network based dynamic modeling. And these two topics comes under supervised learning, we can say. So this first one is basically we will mostly talk on static modeling in a supervisor setting, and this part is basically a dynamic modeling in a, or like system identification in a supervisor setting. And later on towards the end, we will move on to unsupervised model extraction using neural network, where we will discuss autoencoder and how we can extract a static model in an unsupervised setting using autoencoder. And so these work SSNNO and AEO, like these two are like the some research work which I have done in collaboration with the automation group IIT Bombay. So we will briefly discuss these topics as well. So we can start with the neural network. So in general, we can code a neural network as a nonlinear model, and it is inspired from the idea of biological neural network. So which is in the nervous system of humans and animals. So it's inspired from that idea, but currently from it's like so we call it like artificial neural network or like ANN. And so this neural network currently mostly referred to artificial neural network. And in this talk, we will only covering the artificial neural network part. And currently, it's like one of the most popular models in artificial intelligence and machine learning. And the popularity of this model is because of it can approximate any continuous function, either static or dynamic models. So that's why it's very popular. And we will see how we can use how it is possible for a neural network. So in mathematically, we can represent a neural network as a nonlinear composite function. So here as in equation 1. So here this fnn we represent the neural network. So X is like the input to the neural network. So this we can consider as a vector, n-dimensional vector. And this y hat we can consider as the predicted output. So which is like an m-dimensional vector. So this is like the input and this is the output. So the predicted output using neural network model. And this fnn denotes the neural network, and this theta will denote the parameters, like the model parameters or like the parameters of the neural network, which we will discuss later. And here it is like a composite function, and each of these individual functions f1 till fl we can call as the layers of the neural network. And there is one f0 cell. F0 we normally call as the input layer, but this f0 is simply passing the input data. So basically f0 of x is basically x itself. That's why it's not included in the model. So this f1 till fl minus 1. So these we call as the hidden layers, and this fl we call as the output layer. So this is the structure of a neural network. And in this each layers there will be many neurons. So neurons are like the individual functions or like individual components of this each layer. So these circles in this graph is like basically these nodes, or like we can call this nodes. Nodes are basically represents the neurons, and this is like a function, so which will contain we can have arbitrary number of layers in this function, so by adding more and more terms. So yeah, this is the basic structure, and we will discuss this in detail in the upcoming slides. So actually we have studied in maths in school, I think, composite function. What is a composite function? So in general, a composition of function from like, it's like a composition of two, or like we can say more than two functions. So if you have a function f from set A to B and another function g from set B to C, so the composition of g and f, so we can denote it as g of f of x. And this g of f of x will be a function from the set A to the set C. So this idea is basically, I mean, this structure is basically used in neural network as well. And if you see the layers of the neural network, so each of the layers are in the form of a composite function. So we can denote each of the layer fi represent as in equation number 3. So this is also in the form of a composite function where we have this f is equivalent to this ai xi plus bi. If xi is the input, so this is equivalent to f of x, like f of x term, and this g is similar to the sigma I term. So this is like a composition of two functions. So this ai xi plus bi is like an affine function, which is an affine. It's like a weighted sum plus some bias like of the input, and so it's like a linear transformation. And so the sigma is actually the nonlinear function. So the sigma introduces nonlinearity into the neural network, and the sigma we can call as the activation functions. So based on, there are many choices of activation function based on which we can have different possibilities. So now we, in the previous slide, we have seen that in the neural network, there will be many such layers. So we can say it is like a many compositions will be there. It's like composite function which contains all these individual compositions. All right. Now this AI is called as the weight matrix. It will be a matrix, and this BI is called as the bias. So we can see that the sigma I can have mi number of components. So mi basically we denotes the number of neurons in the layer. So we will be having as many activation functions as the number of neurons. So each neuron will have an activation function. So that's what denoted here. And so we normally denote the depth of a neural network by the letter D we can use. So it is basically the number of hidden layers plus the output layer. So that is equivalent to the L. So L we denoted as the number of hidden layer plus the output layer. So there is only one output layer, and there will be L minus 1 hidden layers. And the width of a neural network is basically the maximum number of neurons in a particular layer. So we have to find it like for each layer, for all the layers, which is the layer with the maximum number of neurons. So that is the width of a neural network. So these two terminologies we will be briefly using later. Yeah, so we can just look into the activation function and we can consider an example. So this rectified linear unit, or ReLU, is one of the popular activation function. which is used in neural networks. And this is a nonlinear function. So this basically introduces nonlinearity into the model. And this is, I think, one of the commonly used activation function. And this function we can define as in equation 4. So this is basically takes the maximum of the input value or 0. So it's like a rectifier. So I think we have studied like this half wave rectifier, or like which are like select only the positive half cycle. So this function is basically a mathematical representation of the same system, or like rectifier unit. So here if you see, if the input is negative, the output will be 0. And if the input is positive, so the output will be same as the input. And this is what we can see in this graph as well. So for negative inputs, the output will be 0. And for positive input, it's like it's like a linear function with gain 1. Now we can consider a few examples with the ReLU function and see how it is like how we can have introduced different nonlinearities into the model. So first we can look into the function of a graph of a function which is like a linear function y equal to minus x minus 2. So here we can see that this is like a linear function with the slope minus 1, which we can see in this plot. And so its intercept is actually minus 2. And here we can see that, so this function becomes 0. So if you equate this to 0, we can see that x is equal to minus 2, I guess. Yeah, so this we can observe from here as well. So if we equate this, the output equals 0 when x is equal to minus 2. Now, if x is greater than minus 2, so the output is negative. And if x is less than minus 2, the output is positive. Now, if you take ReLU of minus x minus 2, so basically we have seen that ReLU function will give an output 0 if its input argument is negative. So we can see that whenever this term is negative, so the output will be 0. So that's what we can observe in the second plot. So for all values of x, which is greater than minus 2, ReLU of minus x minus 2 is 0. And for which is less than minus 2, it basically gives the same output as the input. Now we can look into another function, which is like a same linear function initially, 2x minus 4, which is a line with slope 2 and intercept minus 4. And here also we can see that this function becomes 0 when 2x minus 4 equal to 0 or x equal to 2. So which we can observe here. So this function is becomes 0 at x equal to 2. And for all the values of x which is less than 2, this function is negative. So that's why in ReLU of 2x minus 4, we can see for all the values of x which is less than 2, so the output is 0. And for all the values of x which is greater than 2, the output is same as the input. Now we can look at another function similar way. So it's like y is equal to 5x minus 15, which is a line with slope 5 and intercept minus 15. And here we can see that this function becomes 0 at x equal to 3. And for all values of x which is less than 3, the function is negative, the output is negative. So that's why in this second plot, we can see that if x is less than 3, the output is 0 for ReLU of 5x minus 15. And if x is greater than 3, it's like basically the output is same as the input. So these are some examples which we have seen. Now we can just combine all these cases. And so we consider these two cases, ReLU minus x minus 2, 2x minus 4, 5x minus 15. So for which the graph were as in this first three subplots. Now we can consider a weighted combination of these three plots. So which is given in case D. So here is like ReLU of minus x minus 2 plus 0.5 ReLU of 2x minus 4 minus 0.6 ReLU of 5x minus 15. Now here if you just take a weighted sum, so here we can see that, so this first term was like ReLU of this function has this we can call as a fold. So this was like a folded line. So where we have a fold at minus 2. And this was another folded line where we have a fold at plus 2. And this was another folded line where we have a fold at plus 3. Now, if we are taking a weighted sum of these three plots, folded line where we have three folds. One is at -2, another one is at +2, another one is at +3. So this folded line, normally we call it like a piecewise linear curve. So here we got a piecewise linear curve. So basically here we can see that where this line gets folded is decided by these terms, like which we used inside this ReLU. So whenever this input argument becomes 0, so that was like the point where this line gets folded. And so that time that was decided by this parameters. We can call -1, -2, then 2, -4, then 5, -5. So here we got a negative, we can say this, there was a negative slope like after this 3, because we used a negative scaling here, -0.6. So if you use the positive slope, positive constant here, it would have been gone like something like this. The slope would have been increased from this slope. So yeah, that's what we are trying to say here is like, so this function, in this function, so the plot or graph of this function is decided by these parameters like -1, -2, 2, -4, 5, -15. And from a neural network perspective, each of these individual ReLU function we can consider as a neuron. So here we have like, let's say, so here we have three neurons. We have three neurons and we got three folds in the curve. And we can say that here, if we add many number of neurons, let's say if we are adding more number of ReLU terms, we can get arbitrarily like more number of folds in this curve. And we can also decide where we want to fold this line by choosing these terms like these constants. So this first one, constant 5 or like 2 or -1, we were calling them as the weights of the neural network, and this term we were calling as the bias, like -2, -4, -15. So this basically indicates like by selecting the weights and biases properly, we can have a piecewise linear structure which with arbitrary number of folds. Like if you, let's say if you have 1000 neurons in this, if you're adding 1000 neurons here, we can have a piecewise linear curve with 1000 folds at max, like maximum 1000 folds. So yeah, and we can simply, if you see some literature, it is like piecewise linear curves can approximate any continuous function if we add sufficient number of what we can say linear pieces or folds in the function. So this idea we will discuss later on. Yeah. So that's why, so here if we see, if we consider a continuous function, if you want to approximate, we can use a neural network with ReLU structure, ReLU activation, and we can increase the number of neurons in the neural network, and thereby we can able to approximate the function. And now if we look at this this equation, this we can represent as in equation number 9. So where we can see that each of these neuron, like if you consider this first case A, so that is also in this form, for which A2 is basically a constant. It's like A2 is basically 1, and sigma 1 is basically ReLU, and A1 is -1, B1 is -2, and B2 is 0. And for each of these, it's like a single neuron. And if you consider case D, so that also we can represent in this form, for which A2 will be a row vector with all these scaling terms. So it's like it's a row vector which contains 1, 0.5, and -0.6. Sigma 2 will be contained in three ReLU functions. It's like a vector valued function with three ReLU terms, sigma 1. And A1 will be a column vector or a column matrix which contains these weights. So A1 will contains -1, 2, and 5. B1 will also be a column vector which contains these bias terms -2, -4, -15, and B2 will be 0. So now if you see in the initial architecture which we were defined for the neural network, so this thing is in the form of f2 of f1 of x, which is in the form of a composite function. And here we can see that we have two layers. There is one hidden layer and one output layer. So the output layer was basically containing parameters a2 and b2, and the hidden layer was containing the parameters a1 and b1, and there is sigma 1 as well. Sigma 1 was the activation function for the hidden layer. So a neural network of this structure with one hidden layer and one output layer. So this neural network is called as shallow neural network, shallow. So this was the initially used structure. Like initially people were using only shallow neural network for approximating data or data driven modeling. And if we have more than one hidden layer, we call it like deep neural network. So in the past 20 years, like people started using deep neural networks, which was like more than one hidden layers. And so this resulted in the subfield of neural network called deep learning. So where people use neural network with more than one hidden layers. But we have seen that like with only one hidden layer, like with this kind of structure, if we keep on increasing the number of neurons, we can approximate like continuous nonlinear functions. So one hidden layer is sufficient for approximating, let's say, this kind of functions. But with more than one hidden layer, we can have more possibility. Like we can have other what we can say possibilities. So yeah. So far we have discussed with the ReLU function, like ReLU function. There are many other activation functions which are commonly used in neural network. So this is just a graph of different activation functions, and these are like if you see in these plots. So if you just this modulus function is basically taking the mode of the absolute value of the input. Except modulus function, if you look at the other functions, the graph is somewhat similar. There is some similarity in the graph, and so yeah. So but I mean, so here if you see this modular ReLU, modulus, step, signum, these are like some, and saturation as well. These are like some. These are continuous, but it's like not. There is some. It's not like differentiable. So there is some point which is at which it's not differentiable. So this is not like a smooth function. And the last few like sigmoid, swish, and tangent, these are like smooth functions which are like differentiable at all inputs. Yeah, we can discuss this maybe like in the question answer section. Like if you want to. Yeah, after this slide. Yeah, okay, yeah.
So,
Yeah.
Mithun, is
Yeah.
it possible how to choose the active? Even morning also one student asked the question that how to choose the activation functions. Then which problem is there? Any thumb rule is there or?
I mean, I also don't know much. Like I mean, so there are like no thumb rule. I guess I don't know. Like so yeah, it's like it's based on the what we can say. So if you want it to be differentiable, like we can use sigmoid. So and also in sometimes like ReLU has some disadvantage. It's called like yeah, not ReLU. Like all many of this function which was like this output is 0 for this negative input. For if you see ReLU, so it's like the output is 0 for negative inputs, right? And for sigmoid also, yeah, sigmoid also it's like output is 0 for negative inputs. And I think for step also it's like same, like output is 0 for negative inputs. So in that case, like what happens, like if you take the derivative of this output, like this function, let's say, or like the gradient. So for ReLU for negative inputs, the gradient is basically 0. And for positive input, the gradient is same as the slope of, it's like gradient is basically 1. So for ReLU and step, and I think for sigmoid, I think the gradient is basically 0 for like negative inputs. So because of that, what happens is like if you have very deep new structure, deep architecture. So when we are training the model, so we will be solving some optimization problem. So where we will be using these gradients. Like so, this is like a so we were saying that this is like a composite function, which is like a sequence of individual functions.
Okay.
And if you are taking, let's say, the very long neural network, so this gradient can become, so it's like because of this gradient is 0 at the negatives. So if you are taking the product of these gradients, like for maybe for large number of layers, so the gradient can become 0. So which means like this is called like this in literature, it is called like vanishing gradient. So this problem can occur in this kind of activation like ReLU or step or sigmoid, but
Okay,
it
sir.
can be avoided. It may not happen in maybe this modulus or tan hyperbolic. No.
Okay. So we are doing any system approximation or modeling through neural network. If
Okay.
if we are doing any system modeling or any modeling of we are doing with neural network.
Okay. Okay.
In
Yeah.
such
Yeah.
a case,
Yeah.
in
Yeah.
such a case, that means we are doing approximation of neural network of the real plant. In such a case, is it in like a PRB test or something like that we have to do, or any input like? Is there any, because in system identification we do PRB test, na some
Okay. Okay.
like that. Any inputs also we have to change like that. Is there any condition? Is there? That's what I'm asking.
So that also I'm theoretically, if there is any particular condition, I am also not sure. There are so normally what we assume is like the input should be sufficiently rich. So that is like sometime it should
Okay.
contain sufficient what we can say information.
Okay,
So
sir.
there are different conditions called persistence of excitation for I think system identification. But in
Yeah.
general, like if the input contains like let's say input can capture the all non-linearity, like all the non-linearity which is present in the system. So if the input can what we can say input can capture that or like input output data that can capture that information, then we can able to get the actual model information, like actual model.
Okay, sir.
So the basically the input should contain sufficient number of information about the system.
Okay.
Yeah.
Okay. Is there any question from online or anybody? Anybody? Any question? Any other questions?
Sir, my question is, since the graph of step and signum is same, so how can we set that? How can we choose that whether we have to choose step or signum?
Yeah, these step and signum are not commonly used, but yeah, the only difference is like the range. Like if you see step is from 0 to 1 and signum is from -1 to 1. For signum, the minus like for negative values, the output will be -1, and for positive values, the output will be +1. So that is the only difference. Like only difference is like the output range is different. So yeah, like we can say with the signum, this vanishing gradient problem may not happen, or we can say something like that. So
Okay,
the
thank you.
commonly used ones are like ReLU, then sigmoid, then tan hyperbolic. These are like the commonly used one. And this switch is like a recent one. I think this is yeah, it's a recent one. I'm not sure. Yeah, it's also I think commonly used, I guess. So switch is like if you see, it's like a smooth approximation of ReLU. So ReLU, if you see, it's like 0, and for positive inputs, it's like some slope. So here also it's like that, but it's like a smooth approximation. It's not like a non-differentiable at 0. It's differentiable everywhere. Right? And so here, if you look at this ReLU and modulus, these two are like we can call it like non-monotonic. So by monotonic, we means like if we consider ReLU, step, or signum, these are like keep on increasing. So there is no, so the slope is like it will be 0, and after that it is positive. So the function is basically keep on increasing in the domain, and for all these functions. But for modulus, it is actually initially decreasing and then increasing. And for switch also, it's like it's actually initially it's initially decreasing and then increasing. So except modulus and switch, all these functions are monotonically increasing functions. So yeah, this is also a common thing which is used in the literature. So people normally use monotonic functions. So the initial versions of the neural network were only using sigmoid functions, or like functions which are in the sigmoidal. So this is basically the logistic sigmoid function. So the initial versions of the neural network were using the sigmoid function. And after that, so ReLU also become popular. So yeah, this is the case. Yeah.
Thank you, sir.
Okay. Yeah.
Okay, I think somebody from the online they are asking. Yeah, you just ask. Sunil. Oh, any other query from online? Any other query? Shall we move on? Yeah. Okay, sir. Please move on, sir.
Okay. Okay. Thank you. Yeah. So what we have discussed is like it's like there are some theoretical results. So basically, what we were saying in the previous slides was it's like you're saying that using a neural network we can approximate like any continuous nonlinear function. So there are many theoretical results on this aspect, and these are known as universal approximation theorems. And two directions of universal approximation theorems were like there are I mean the research were like proposed, like theorems were proposed. One is called arbitrary width, and another one is like arbitrary depth. So the arbitrary width case is basically it's like a neural network with a bounded or like finite bounded number of layers, but the number of neurons in a layer can go arbitrary. So that is the case. And in the case of arbitrary depth, it is like a neural network with a bounded number of neurons per layer, but the number of layers can go arbitrarily large. So this second direction, like after the introduction of deep learning, so this second direction got a lot of interest. Like so because like the depth is like how the depth is affecting the approximation capability. So, but we will just only look at this one theorem, which is like a very popular and initial versions of the universal approximation theorem. So this theorem, we will just briefly summarize. So the basic theorem states that the neural network of this kind of structure, like it's like a shallow neural network or like a neural network with one hidden layer. So I think we have in the case of with the ReLU example, we were considering ReLU a neural network with this kind of structure. So if you are considering a neural network with this kind of structure, it can approximate any function, let's say any nonlinear function f of x. So with a accuracy like or like with an error which is less than epsilon. So epsilon can be any arbitrary positive number which we desire. So if you choose any epsilon, which is like any arbitrarily small, any small value, we can find a neural network which can approximate that function in a compact, like in a bounded set. So that is like the basic idea of this theorem. And later on, similar theorems were proposed for a deep neural network as well. But we can consider this as a one of the benchmark result. And because of this, what happened is like neural networks can be considered as a generalized models, so which can be used for any application, or like if let's say if the data input output data contain any kind of structure, any kind of nonlinearity, we can possibly we can approximate the actual relationship using a neural network. That's why like they are very much popular. So it's like it can approximate any function, any continuous function. So functions which are like static functions. So here by okay, yeah, we can just by static what we meant is like, so the output of that function at a particular instant is only depending on the current input. So we were discussing functions in the form of y is equal to f of x, where y and x are like it can be scalars or vectors. It can be multivariate, but the time instant when this y and x is considered is same, like both are at the same instant. So that's what we were calling like a static model. So in other words, the current output is depending only on the current input. So that is in the case of static model. Next, we will be moving on to dynamic modeling or like system identification. So in the case of dynamic models, so the current output depends not only on the current input, or it can depends on the past inputs and also past output as well. So that's why there is some time is coming into the picture, and this kind of models are called dynamic models. And yeah, we will be briefly discussing on this dynamic modeling using a neural network. So yeah, as we have just already discussed, static model is like in which all variables in the model are at the same time instant. But in dynamic, so it will represent time dependent relationships as well. So in the case of there will be some time. So and one of the most popular or like recently one of the popular models of dynamical systems is the state space form. So I think I assume most of them are like most of the audience are familiar with the state space model. So this is like a state space model in discrete time. So and similar models are there in continuous time as well. But here we are considering only model in discrete time. So here this k indicates the time instant. So xk is basically we call it like a state vector, and uk we call it like a control vector or like input vector, and yk we call as the output vector. So basically this means like the output vector at the kth instant, and this means like the state vector at kth instant. So this k we can it's like if you are considering a continuous time system and sample it at a particular sampling rate, we get this kind of discrete time states. So it's like basically the state at 0th instant. If the sampling period is like 0.1, let's say, this denotes state at 0th instant, 0.1th instant, 0.2th instant, like that. It is like that. Yeah. Now, yeah, this is like a general structure of a nonlinear dynamical system in state space form. So here is f and g. Basically, f we call as the state function, and g we call as the output function. So these two are like nonlinear functions which represent the nonlinearity or like the system dynamics. So if we consider f as a linear function, we have a linear system in discrete time. So in that case, the structure is in the form of a like it is xk plus 1 equal to a xk plus b uk, which is like a linear system. But here we are just considering a nonlinear model, and this state space neural network is like a architecture which is proposed in this paper. So here what they used is like they just approximate this f and g functions using a neural network. So this f we can approximate using fnn, which is a neural network, and g we can approximate using gnn, which is another neural network. So this is like the structure of a state space neural network, and which is a very it's like not in computer science community. This is not that popular, but in control system design, I think this state space neural network is like a popular model, because like in many of the modern control systems algorithms, we will be using this kind of models like state space models. For example, in the case of model predictive control or sliding mode control or like optimal control, everywhere like adaptive also, I guess. So people are using state space models. So that's why, because of that, this kind of architecture are also, the state space neural network is also increasing and gaining the attention.
Mithun sir,
Yeah.
Mithun sir, why that GN is there? Why? Because anyway, it's approximation of system. Now, why two networks are there? One for state, one for output. It is necessary.
In this structure, it is like it is basically trying to approximate is the nonlinear state space model in this form. So this f function, we need one neural network, and for g another neural network. So this g is like basically some function, like let's say normally I think it can be a linear function. So normally I think we take so this output and state, this relationship is like a linear in many of the most of the practical cases. So if it's like a linear combination of the states or like some subset of the states, like which we are actually measuring using some sensor, so that will decide this output equation. Yeah, normally I think it is linear. So in that case, we don't need so we can take it as a linear time. We don't need a neural network to approximate here.
Okay.
Yeah, I think in the initial versions, like initially there was initial versions of I think initially it was like called so the state space neural network we can consider as a special case or like a subset of recurrent neural network. So in the recurrent neural network, the structure was like there was no, this output time was not there. So it was basically like it was like an input output model. So only this time is there. So here we can consider this as yk plus 1 hat. Yk plus 1 hat is basically equal to fnn of yk hat comma uk. So it is like the it's like an input output model. So where we can approximate the input output relationship with the dynamic model, and this theta will contains the parameter. So that was the structure of recurrent neural network or RNN. But here we have this is also like a subfield, but here we have an additional, or we can call a hidden variable, which is like the state variable, which is not what we can say, for which the data is not available. We only have the input output data, like we have UK and YK, but we don't know the states. So states are like some hidden variables or like some hidden dynamical variables of the system.
Okay, sir, please go.
Yeah. So here is like a block diagram of state space neural network, and so here this is like a pictorial representation of the previous equation. So here this fnn will takes uk and xk hat, and it will predict xk plus 1 hat, which is basically the state at the next instant. And here this delay is not delay here, then it's basically we will get yk plus 1 hat. So here we just try to get the same equation. So like we just added a delay here, and we get xk hat, and if we give that to gnn, we get yk hat. So this was the output equation term, and this was the state equation term. So where we have a delay, if we delay it by 1 instant, we get xk hat, and this is like a so this entire thing we can call like a recurrent neural network term, recurrent neural network. So basically the output is depending on the current input and also the previous input. Like that is like there is this kind of connection. There is a feedback connection here. So this kind of connection is called like a recurrent connection. So yeah, so this entire architecture we can consider as a special form of recurrent neural network. Yeah. And because of this delay, or because of this feedback connection or like recurrent connection, this model becomes dynamics. So where we can see that this xk plus 1 hat is, or like xk plus 1 depends on the previous values of the input, previously past input and past value of the state. So this is like a dynamic model. Yeah, now we can define the state and output. Like the first one, this FNN, we are calling the state subnetwork or like state neural network of the, and this GNN is like the output subnetwork of the SSNN. So these two we can consider as deep network with this kind of structure. So in the state subnetwork, we are considering L number of layers, and in the output subnetwork, we are considering M number of layers. This structure is same as the initial one, like initial network, neural network. So which we discussed initially, the structure is same, and for each layer, the structure is also same. It will be containing an activation function, and there will be a weight and a bias step. Now let's say we have an input and output data, which is in the like we have a finite number of samples of input and output, which we can represent in some matrix form as in equation 16. So this U1 is basically the input vector at first instant, second instant till capital N number of instances are there. Let's say the output is also available for this time instance. So like for the, in the case of system identification, so all we assume is like this data is available. So we have some, this kind of measurements are available. And then what we needed, our task is to, if we know this data, so how can we find a model which can predict this output given for this input? That is the objective. And in our case, the model is in the form of a state space neural network where we need to find FNN and GNN. Basically, we need to find these two functions. That is, or like the parameters of these two functions. Here by parameters, we call this, we means like this weights and biases. That is what we needed to do. And this activation function, we normally choose as same for all layers. Like if you're considering ReLU, we will use ReLU in everywhere, like in the entire neural network. Or if you're using sigmoid, we will be using sigmoid throughout the neural network. We will not use different. Yeah, I mean there are some work with different activation function, I guess, but mostly we use same activation function in all the hidden layers. And in the output layer, normally we can use either linear without any activation function. We can just use only the linear terms in the output layer. That is also a commonly used practice. Yeah, now like if we know this kind of data, so how we can find a model. So that is like what we are looking at. So we can just denote the predicted state and output data using SSNN as in equation 17. So this x hat will contains x1 hat till xn hat, and its y hat is basically y1 hat till yn hat. Now we can see that if we know the initial state like x1 hat and also the control sequence, this control sequence will be anyway available to us, this U matrix. So if we know initial state condition and the control sequence, we can find this x hat. That is possible. So how it's possible? Because like yeah, we can use this FNN function. So we can, let's say this FNN we can initialize with some parameters. And if we know this, if we know this FNN, then like x1 hat is already, let's say, assumed to be available, and this x2 hat will be FNN of x1 hat and u1. So this u data will be anyway available to us, and if we keep on applying these functions recursively, we can find all the states x till xn hat. So what I'm trying to say is like if FNN is not, like if we have some initial parameters for the model, we can find this x hat using the initial parameters. Yeah, also we also need to know the initial condition. That is also an important thing. Initial condition of the states. So which we also may not be known in most of the practical cases. So we can, this also we can initialize using some random value. And then we get an initial value of this x hat. That is the case. Now if we know x hat, like we can find y hat, which is basically this y1 hat is basically GNN of x1 hat, and y2 hat is basically GNN of y2 hat. Sorry, GNN of x2 hat. So basically, if you give it to the output neural network, we get the output subnet neural network, we get y2 hat as well. Now, if we know y hat, we can find the loss function of the SSNN, which is basically as in equation 19. So this is basically the error between the actual output and the predicted output. So here, this time we can expand it as a sum of square. Like it's basically y1 minus y1 hat square, like norm square plus y2 minus plus y2 minus y2 hat square. It's like this. We can expand like that. So we have seen that y hat is basically GNN of x hat. So what I'm trying to say is like if you know, if we initialize this FNN and GNN with some parameters, we can find value of JY for that particular parameters. And in the optimization problem, what we are trying to solve is like we are trying to find the optimal set of parameters theta, which minimizes this loss function. So this theta will contains the parameters of the f function, like f state neural network and also the output neural network. So this will contains all the weights and biases. So yeah, this is like an optimized nonlinear programming problem which we can solve. It's like we can, so let's say if we initialize theta with some value, we get some jy. Then we update this theta using some approaches like gradient descent or like some numerical Newton method or like some numerical solution method. We can update this theta parameter. We get a new cost. We will try to update this theta in such a way that the cost is decreasing. So like and we will eventually converge to some optimal set of parameters. Yeah, so that is the idea here. But we need to have some initial state condition, which is also yeah, there are some challenges. One of the challenges is like this initial state is not known, which is like one challenge. And another challenge is like this state dimension. So we don't know how many states are there in the network, or which we also call as the model order. So the order of like the order of the model is like not known in practice. Like I mean, in state space model, like in conventional first principle models, we know how many states are there in the model. But here in our case, we are assuming only the input-output data is available. We don't know anything about the system, like first principle information is not available. So in that case, we don't know the model order. So we don't know how many states are required for capturing this or like predicting this output accurately. So that is another challenge in this state space neural network. Yeah, and there are some theoretical results. So this is like I mean, this we don't need to go in detail. We can briefly. So this condition is called like this condition is normally used in control system or like nonlinear systems, which is called Lipschitz condition. So this condition basically says that this function which we are considering, this f and state and output function, is like sufficiently smooth, or like what we can say, the slope for this function is bounded for any points, like any two distinct points. So the like the gradient of this function is bounded, or we can say something like that. And if this f and g are sufficiently smooth, like or like continuous, yeah, there is one lemma, like these are like a theorem. This we can consider as a universal approximation theorem for state space neural network. So this theorem basically says that if there exists like for any systems, let's say for any nonlinear system with the f and g, if the data is generated from this f and g, there exists a state space neural network with an appropriate initial condition, so that the output prediction error is bounded by epsilon. So this is the result. So we can approximate it by any arbitrary degree of accuracy using a neural network. So that is the this lemma basically says. So this is basically the universal approximation theorem for state space neural network. Yeah, maybe we can stop here, and if there is some questions, we can briefly go through.
Yeah. Is there any queries? Any queries? For online people, any queries?
No, sir.
Okay. Yeah, and okay, this is like already there in the literature. The state space neural network was, I think, for maybe more than 20 years it is there. But yeah, we were saying that one of the challenges, like we don't know the initial condition, and another one is like the system order, or like the model order is like unknown. So yeah, this led to our next topic, which is state space neural network with ordered variants. This is one of the work which I have done with the collaboration with the IIT Bombay Automation Lab. So this in this work, what we are trying to, and this is also based on one of our another work on autoencoder, which we will discuss later. So here, what we were trying to achieve is like we were trying to order the states in terms of their variance. So that is like the idea. So this is like same as state space neural network, in which the predicted states are ordered in their variance. So that is what we call SSN and O. So and this notation, I think we can skip it. It's basically same as the state space. We just added some O here to indicate that it is like the states are ordered in their variance. So yeah, in the now, like if we have this FO and GO, these are like basically state neural network or state subnetwork, and this is output subnetwork. And here this theta FO and theta GO, these are basically the parameters of the state and output network. So yeah, this will be basically the weights and biases. Yeah. And using this, we can define the predicted output sequence and predicted state sequence. So this XO and YO hat. Now using this, we can define the output prediction error for SSNN now. This is only the output error time, so which is similar to the SSNN. So this is like a weight sum of output, actual output minus predicted output. But in our modification, we just modified this term. We just defined JO or something. This is like a weighted sum of output prediction error. Then there is another term. This J2 is like one of the contribution, which is basically the variance regularization term, or like state variance term. And this J3 is commonly used. It is like a weight regularization term, which is normally used in neural network models. So in this J3 is basically take some norm of the weights, or like the parameters in the model. But this J2 we try to include in the model in order to achieve ordering the states in terms of their variance. And this J2 we can expand as in equation 27, where we can see that it is like a weighted sum of the state variances. So here Vxo1 basically means the variance of the first state, and Vxol means the variance of the Lth state. Like basically, we are assuming that we don't know the model order, so we can select it at some arbitrarily large value, which is denoted by L. And this Vxol basically denotes the variance of the last state in the model. And here, if we select, let's say, this W1 to WL, which are elements of this weight matrix W. So if you are keep on increasing WL, like if WL is very large, then in that case, after solving this optimization problem, this variance will be very small. We can obtain. Yeah, but this is like a trade-off which we have to this W we have to select properly. So if you are increasing this W, it may affect the prediction error time. But yeah, this is like the structure, and the optimization problem will basically we need to minimize this loss function. We have to find the optimal parameter theta O. So this basically contains this state parameter, output network parameter, and also this is basically the initial condition. So here we are only also considering the initial condition as a decision variable. So after once we solve this optimization, like we get this theta or like the optimal values of this parameter. Then using that we can define a state and output neural network, and that is the overall idea. Now, yeah, we were saying that in this SSNNO, the states will be ordered in decreasing variance. So what we observed also in most of the cases, after some value, the states will become very small. It will be nearly zero. So let's say if we are denoting the small letter s for the number of significant variables in the model. So by significant, we means like the variance is like has some significant value, which is also or which is greater than delta. So delta is like some tolerance value which we can select. So if the variance is greater, if the variance of the state is greater than delta, we are calling them as significant. And if it's less than delta, we call them as some residual states, which are like nearly zero. So the variance is zero. We are assuming the variance is zero. And this was our idea for identifying the model order. So what we done is like if we consider the residual variables for which the variance is zero. So the variance zero means like this is like a constant term. So the residual terms we can replace with their mean values. So that was the idea. So because it's like the variance is zero, and if we replace those variables with their mean values computed over the training data, so it will not affect the output prediction error. So which basically means like so we can achieve some model order identification or like model order reduction with this approach. And in the model, we only retain the states for which, or like we only retains the significant variables, or so which means like the model order will be same as the value of small letter s here. And let's say if we denote the prediction error with this reduced order model as JYS, and we have some theoretical results which says that there exists an SSNNO for which the prediction error is bounded by epsilon. So like for any values of so if we can say, let's say the actual order is like unknown, but if we select some very large order which is greater than, let's say if the actual order is 10, and if you select the model order as 100, for any value of s between this value, this prediction error will be bounded. And we can also sometimes, most of the time, we can achieve, we can reduce this value of s can also be reduced beyond n, or it can be lesser than n. So in that case, we can achieve model order reduction as well. So otherwise, we can identify the model order, which is sufficient for approximating the output. Yeah, this is just a numerical example. So in which this is like a simple example. We consider a second order system, and which is called continuous state tank reactor, or CSTR. And so we consider that so this is like state space model in continuous time. We just discretize this model and generate the data using this model. And so the parameters are chosen like this. Then here in this first plot we have the training data. So this yk is like the actual data for the training, and yok hat is basically the output predicted using the SSNNO. So here we can see that in the training data we added some noise, also some small Gaussian noise was added. But here we can see that the model is able to predict the data for the training case, and this is for the testing case, which is also able to predict it sufficiently accurate. And we tried it using some step input to the data, like the system. And so here we can see that the step response is also like the model is able to predict the output. And this is like some table where we were comparing it with the SSNN. So here we can see that for SSNN now, the variance is like ordered in decreasing variance. So this VXO1 is basically the variance of the first state, and VXO3 is the third state. So here we just selected the model order, or LS3, and just after training SSNN, we got these as the states like variances. But in SSNN, we can see that these are like not ordered. There is no order. And also all three states has non-zero variance, which is also we can observe here. But in the case of SSNNO, like for the third state, the variance is 0, which means like only with two states we can approximate or we can model the input-output relation. And the training error and for the testing error, these are like these are also somewhat similar. So here it is like same as the SSNN. And here another example for fourth order model. So here also the same thing we can observe. For the third and fourth states, the variance is 0. So these two states we can remove. And for the second state also the variance is very small. So even if you remove the second state, or like if you replace the second state with its mean value, that is also does not affect the output that much. That's what we observe. In our simulation, that's one thing which we observe. So here, but yeah, in general, here we can see that the actual order, which was like the actual system was second order. So we were able to identify the actual order of the system using this SSNNO. But in SSNN, this is not the case. So here we can see that all the four states are having non-zero variances, which means like all four states are significant in this case. But in our case, like only two states are sufficient. Yeah, so that is all about this SSNNO idea. Maybe we can just stop here, and if there is any question, we can briefly go through.
Yeah, any query? Yeah. It's from your lab. Is he able to listen?
Yeah,
Hello,
I can hear. Yeah.
Hello, Mithun sir, this is Vikram.
Yeah, hi Vikram. Yeah.
So, sir, just I have a general question. So, whatever you explained about SSNN and SNNO, so these are what you're presenting is a typical algorithm development, or these are the steps one has to follow to solve the problem using already developed these algorithms. So, is my question clear to you?
This SSNNO was like some algorithm which we have developed. It is not like there is no like standard method, I guess, because in SSNN also there is no standard steps to follow to identify a model. So one of the advantage which we observed is like, so he actually in practice, like if you consider system identification, the model order will not be known, like unless we have some first principle information. So how to find this may not be a challenging case for like small order systems, like but in this simulation we consider a second order. So in that case it may not be a challenging problem, but in practice for some large process, or like where there are many hundreds of variable, this is like a very challenging problem. Yeah, but currently we haven't implemented it on a large process, but that is like one direction. Yeah, but in that case it might be useful, like this SSNNO, if we can order it in terms of their variance, like but yeah, it's like a very challenging, because we need a lot of training of the model, and there are some parameters. Yeah.
because the people we are just a person like me who's not from a control background, who hasn't done much in the control and solving some problem using neural networks. So all these steps, when I have to put a lot of effort in even memorizing these steps and to follow and to solve the problem. So is it literally challenging, or with the practice things one can really solve these problems just by practice?
Yeah, it's challenging, and for this, yeah, I mean, but I think it is, yeah, it's like if you consider a particular application, I think it is possible to identify a model, but we need
Mhm.
to train the model, and if it's like a very small number of variables are there, then it's not challenging. Like we tried with some other, it's like second order or third order, because in the theoretical and the literature, control system literature, mostly people use models up to fourth order or fifth order like that in research direction.
Mhm.
So in that case, it is not that much challenging. But if we
Mhm.
consider a process, a chemical process, or like some where there are many variables,
Mhm.
currently, I mean, I'm also not sure whether we can able to train a model, but it might be possible, but it might be very challenging if there are
Okay.
very large number of variables.
Okay. Thank you, sir.
Yeah, thanks. Yeah, thanks.
Any other query? Any other query? So, Mithun sir, if we are starting with, because we don't know the system identification, that's why we are going for neural network modeling, na?
Okay.
At that case, how come we know the ordered variance? Because you want to compute the
This
at that time.
variance we can compute from the training. Like once we train the model using the training data, we will be computing these variances.
Okay. Yeah.
Yeah.
Okay. Any query from the online people? Any query from the online people? Okay.
Yes, sir.
Yeah. Any query?
Yes, sir.
Yeah, please ask then.
Sir, if we want to create a model for some application, and let's say the model depends on, let's say, 5 parameters, but we know about only 3 parameters, and we can measure only 3 parameters. So we'll be able to create model using 3 parameters only.
Yeah, I mean, so whatever we know about the process, or like let's say this first principle information, or like the model information, we can include that in the model. Let's say, and the remaining part we can model using neural network. That is also possible. So here, like if you consider not like using any algorithm. So here, if you consider, so we are calling this as f, right? So in this f, we can select some known terms which we can call like some f0 or something. And let's say, so it's like f0 of xk and uk, and there is some unknown term which we can call like some f1 or something. So that f1 term we can approximate using a neural network, and whatever is known that we can keep as separate. So that is also, in that case, we just needed to find some residual. So, like what is the no, we just needed to, this part we will not train in the model. This is like a fixed part, this f0 term. This f1 is like something which for which the parameters we can train. So that is also possible. Or
Okay, sir. Thank you.
also this physics informed neural network is like a physics informed neural network was like a recently popular area. And there is this physics informed SSNN, like physics informed state space
Hello.
neural network is also there. Hello.
Yeah. Please continue.
Yeah. So that is also there. So there also people try to include some model information in the training. So that is, I mean, so I haven't worked in, but it's like an area.
Okay.
Yes, sir.
Any other query from the online people? Any other query? Okay. Okay, Mithun sir. Thank you for your wonderful sir insight thoughts on neural network modeling.
Okay.
State space.
Yeah, we
So-
can. Yeah.
So the remaining, Sir has several contents. Sir would be sharing his slides also. Okay, and Sir will continue on Friday or some other time. Okay.
No, if time is there, I can. I mean, it will take only. It is not only for some 10-15 minutes. I think you can finish now itself. That is also possible. Like.
Okay. Yeah, okay. Yeah, okay, sir. You please go ahead.
Okay, yeah. So this part is basically on unsupervised model. So this, I mean, so here we will try to, so, and this idea which we are going to discuss is same as the ordered variants. So, but yeah, this is like some similar idea. So where we use the same idea in autoencoder. So that we used for unsupervised model extraction. So that was the this rest of the talk. So that we can quickly go through. It's not. Yeah, in unsupervised learning, so what is the difference? We don't have any labels. So all data we have, we can call it like some input data. So in the supervised case, we are having some input and output. So which we are calling either X and Y, X for input, Y for output. Or in control system terminology, we are calling U and Y, U for control input, Y for output. So that's what we were considering in the case of supervised learning. So in unsupervised setting, we don't have any input. So all the data which we have, we can call it like some input. Like all we have is input. There is no output or there is no label. So that is the difference in the case of unsupervised case. And in general, so we can say that real world we will be if we have high dimensional data, so it is most likely to concentrate in the neighborhood of some small lower dimensional manifolds. Or so here by manifold we means like some nonlinear curve. And this is called as unsupervised learning hypothesis. And this resulted in a subfield of unsupervised learning known as dimensionality reduction. So in dimensionality reduction, the problems, like the two problems which are of interest is like one is called feature extraction. So where we are trying to extract low dimensional features from the high dimensional data set. So let's say if we have a data set containing thousands of variables, so how we can extract let's say some important features, like let's say some 50 variables or 20 variables out of this 1000, that is called feature extraction. And another one is called model extraction, so in which we are trying to identify the relationships between the variables. So that is like a model extraction time. So this is like, yeah, so we can just look into dimensionality reduction. And in the first, we will briefly go through this model extraction, or like using in the linear setting. So that is also called, that is for that people normally use this PCA or principal component analysis. So in PCA, let's say if we have an input data, which we can represent as in equation 35, which contains a set of input vectors. X1 is the input at the time instant 1 till xn. So here all the variables we can call like there is no label. So this is like an unlabeled input variable. Like this is like all variables which we are collected from the process or like system of interest, problem of interest. Now in PCA, what we are trying to do is like yeah. So what we are trying to do is like we will trying to find a linear transformation, and we will try to transform this x into some other latent space. So the latent space we can call it like so some latent or like some transformed vector, which we can call as this y1. And our objective is to reconstruct this original data from the transformation. So this, that the reconstructed input we can call like x hat. Now in PCA, so PCA uses a linear transformation. So this, that as in equation 37. So here this x is like the input vector, y is the output, y is the latent vector. So which we can consider as a linear transformation of the input. So this P is like the transformation matrix which transform x into y. And then from y, we will reconstruct the original input. So for that we use this, so that we can use this equation 38. So here this P we normally choose in way that it is like an orthogonal matrix, orthonormal matrix. So in PCA, the original idea is like how to find this optimal P so that the reconstruction error is minimized. And also this P should be orthonormal, which means like it is like P transpose P should be equal to identity. So yeah, now if we replace x with this this equation, so here we can see that this is like an optimization problem which we can solve for finding the optimal P. We can just briefly discuss. Actually, in literature, PCA was mostly used for feature extraction. So where, let's say if the original data contains some 1000 variable, we will try to find some linear combination or like some optimal values of the combinations of the input, which we can call like y. So this y can be considered as some features which are extracted from the input original data. So let's say if x contains 1000 variable, we can may reduce it to maybe 100 or lesser number of like maybe 10 variables, some based on how many variables in the original data are like linearly related. So this is the idea of PCA, and in the aspect of dimensionality reduction or like feature extraction. Now, if we consider model extraction, in the case of model extraction, so what we can say is like in PCA there is one another feature which is like so this latent variables will be ordered in decreasing variance. So that is like it is because the variance of these latent variables will be there. Yeah, if you go through the literature, the variance of these latent variables will be the eigenvalues of this covariant input covariance matrix. So they will be ordered in decreasing variance. That is another thing. Yeah, now we can just look at this figure where we have some illustration where PCA is useful. So here we can consider a two-dimensional data set where we have variables x1 and x2. And the variables, let's say the variables are aligned across this, oriented along this line in red color. So here we can see that most of the data points are along this line. And maybe due to some noise or something, it is not exactly on the line, but it is around this line. Now, if we consider two directions, one is P1 vector along this direction, which is along the line, and another one is P2, which is orthogonal to the line. We can see that most of the variation in the data is along P1, and the variance of the data along P2, or which we can call like Y2, or for Y2, the variance is like nearly 0. So here, if you look at if all the data points are exactly on the line, then variance of the data along P2 will be exactly 0. But here, maybe let's say due to some noise, it is not exactly on line, but it's nearby the line. So the variance of P2 is, we can say, small. And if it's very small, if you are assuming it as 0, in that case, what we can observe is like this Y2, or like which is basically P2 transpose X from the previous equation. This P2 transpose X will be equal to 0, which we can observe in this case. Or this we can geometrically, or like if you look at all the points on this line, which we can see, they will be orthogonal to this P2 vector. So their product will be inner product will be 0. That we can that is basically this relation. This we can generalize for an arbitrary case where we have let's say n number of variables. Let's say the first p variables we are having variance, significant variance. And let's say the remaining r variables are having, or not r, remaining n minus p variables are having nearly 0 variance. So then what happens is like the variables with the 0 variance, we can replace it with their mean, or it means the mean is like assumed to be 0 if the data is like mean centered. So if we are replacing this term with 0, what we get is like PR transpose X equal to 0, which is like a relationship. So this we can consider as a linear model in an unsupervised setting, which contains n minus p relations. So here, if we just have a data like unlabeled data, we can apply PCA, and then from the latent variables with the 0 variance, we can extract a linear model. This is the idea, and this we can graphically represent in this figure. Let's say we have an unlabeled input data, and we are reconstructing it using PCA. And if we look at the latent variables or the transformations with the significant variance, we can call them like principal variables. And the latent variables with nearly 0 variance, we can call them residual variables. And these residual variables will basically result in used for extracting a linear model. And the principal variables we can use it for feature extraction. So these are like with significant variance. So they will capture the information in the data set. So this we can use for features. So in our approach, what we tried is like we just try to extend it in a nonlinear setting. So we just replace this linear transformation using a nonlinear or like a neural network and try to do the same thing. And this is like what we are briefly going to discuss next. So it's like the same idea. We just replace it with using a neural network. So, and this autoencoder is like already existing in the literature for more than 30 years. So in autoencoder, it's like a nonlinear version of PCA. So where we have an input data, we transform it into some latent space using a neural network, which we can call as encoder function. And we will try to reconstruct the original data using another function called decoder. So this encoder is like basically it's a neural network or like a sub network, which takes the input, transform it into latent vector, and this decoder takes this latent vector and reconstruct the original input. So this is like these two we can consider as two neural network, and this theta e and theta d are the parameters of the neural network, which are the weights and biases. And this optimization problem is basically trying to find the optimal values of the theta e and theta d, which minimizes this reconstruction error. Yeah. Now in our yeah, but in this autoencoder also, we don't know how, like in traditional autoencoder, this latent variables will not be ordered in variance. So it will be like similar to SSNN case. So there is no ordering in the latent space. So that's why we propose this idea in which in this work. So we try to introduce ordering in the latent space. And this idea is similar to SSNN. We can maybe briefly go through it. And the structure is same as, so we have an encoder and decoder functions, and both of them are in the form of a neural network. And what we try to do, so we have this reconstruction error, which is there in the traditional autoencoder. This is like reconstruction error between input and reconstructed input. And this third term is also standard, which is like a weight parameter regularization term. And the second term is what we proposed. And here, this also we can expand as a linear combination of the, or like weighted sum of the latent variables. And by properly selecting these weights, Q, Q1 till Qm, we can order the latent variable in decreasing variance. And so here, this optimization problem, we try to find the optimal value of the parameters theta, which contains all the weights and biases of this encoder and decoder network. And let's say by solving this problem, we were able to achieve ordering in the latent space. So this y variable we can, so here we just denoted the encoder and decoder in a simple way, and we just use linear functions in the output layer. And let's say this yp and yr, let's say this yp means like the latent variables with a significant variance, and let's say yr is like the latent variables with the zero or like nearly zero variance, which we can call like residual variables. Now what we can say is like this yr in this equation, in this yr term we can replace with the, because it's like variance is zero, we can replace it with its mean value. So that basically results in, so this yr, or like what you can say AER, so this the rest of fe minus 1 till f1 of x. So here we just replace it with the yr bar, so which is the mean of yr, and that will equal to 0. So basically we just, or we can just write it like yr bar equal to this term. So this was like the model. So we got a nonlinear model in an unsupervised setting. That is this idea. And we also extended this idea using a ResNet, which is like a similar idea, but it's like a slight modification. In ResNet, we can have a skip connection, which is as in this figure. So this is the idea of ResNet. So it's like a feed-forward neural network with a direct skip connection. And this is a recently introduced architecture. And we just replaced this idea with the ResNet AEO. And there also we were able to extract model information. And in a simulation, we can consider a simple 5-variable data set, which contains 2 nonlinear relationships. So these are the, let's say, these are the relationships. One is like with sine term, and another one is with the tan term. So let's say, and we just generated the data using these relationships, and we just use the simulation parameters as here. Now with PCA and so we just tried to find the variance of the latent variables, and we also tried to extract a model using all these models. So in PCA, we can see that the latent variable variance are decreasing in variance, So it's like this has the largest variance, which is like variance of the first latent variable, and this is keep on decreasing. But all 5 variables are having zero, like non-zero variances, which we can observe here. And for traditional autoencoder, also this is the case. Like all 5 variables are having non-zero variances. But with this AEO and RAEO, we can see that after 3, and this is ordered first. It's like ordered in decreasing variance. And second, like the variance of the 4th and 5th variables are 0, which we can observe here. So which means like we were seeing that in the original data, we had like 2 nonlinear relationships. So we had 5 variables with the two nonlinear relationships. So, which means like we have only 3 independent variables. So 2 variables were some dependent dependent, like nonlinearly dependent on the other variables. So here we can, and here for the RAE also, for the 4th and 5th, the variance is nearly 0. And this is like some error with for the training and testing data with the identified models, which we can just, which we can see that for this AEO and RAEO, these are small. And this is just an illustration where we can see this, we just plotted x1 versus x4. So in the original equation, we had like, there was a sinusoidal term, x4 is equal to some sine of x1. So which we can observe here. So here is red dots are actually the actual data, red dots. And these blue dots are actually the data or like the output x4 predicted using the model, which is extracted using ResNet RAEO. Or like for AEO also, we obtained some similar plots. And this green one is for PCA. So here we can see that the model identified in PCA, we only got a linear model or linear approximation of the relationship, because like in PCA, all we can achieve is like basically a linear model extraction. But the actual relationship was nonlinear, which we were able to extract using our this ResNet AEO approach. Yeah, these are some conclusions, like concluding remarks. We can say the performance of these models like SSNNO and AEO depends on the parameters, unique parameters. And we are also looking for works for where we can design these optimal parameters or some tuning strategy. And we have some theoretical guarantee which we are working on currently. And also we are also looking for this in unsupervised dynamic model extraction. So this AEO was like an unsupervised static model extraction. So can we able to do it in a dynamic setting? That is also another direction. Yeah, I would like to thank my collaborators, Dr. Parag Patil, Professor Mani Bhushan, and Professor Sharat Bhartiya in IIT Bombay Automation Lab. And also I would like to thank all the lab members of Automation Lab and also IIT Bombay. And I would like to thank VNIT for inviting me and giving this opportunity. Yeah, that's all. So yeah, thank you all. Thank you for listening to this talk. Yeah, if there is any question, we can go through it now.
Any question?
Yeah, any queries? Any queries? Online people, any queries? Okay. Okay. Thank you, Mithun sir, for joining us. We would be grateful for your contribution at here for this GAN course. So you can meet. I hope Mithun sir is well known. You can able to check whatever you have queries. You can able to discuss with him in offline also. You'll be very happy to share your thoughts with you. Okay.
Yeah, thank you all. Yeah, my mail ID is also there. I think this PPT I can share. So if anyone like to have any queries or any discussion, I will be always available.
Thank you, sir. Thank you for joining.
Yeah, thank you all. Thank you. Bye.
Yeah. Okay.
Thank you, sir.
Yeah, thank you, Jayvind. Yeah.